Okay, thanks for joining, everyone. We're just going to let let more people join, and then we'll start in a few minutes. Thank you to everyone new that's joined. I'm just going to give it one more minute and we'll start at 3 past. Okay, thank you for joining this webinar on jet fuel quality organised by Transport and Environment. I'm Marta van der Graaf from the aviation team at Transport and Environment, and I'll be your moderator for the webinar this afternoon. In terms of housekeeping, please use the Q&A box on the left side of the screen to send any questions, not the chat function, so we can better monitor the questions that we're receiving. When sending questions, please clarify who you would like to address your question to. There will be opportunities for questions following the presentations by Jasper Faber and Carlos López de la Osa, and following the panel discussion. We will do our best to answer as many questions as possible. This session is being recorded and presentations will be distributed after the webinar. To kick off today's session, I would like to introduce you to Matteo Mirolo, Sustainable Aviation Fuels Lead at Transport and Environment, to give an overview of the topic of improving jet fuel quality and what this means for the non-CO2 effects and air pollution caused by aviation. The floor is yours, Matteo.
Thank you very much indeed, Marta, and good afternoon, everyone. Very nice to see a lot of people reunited today to talk about this important topic. Maybe just a quick caveat before I start. I'm a lot of things in this life, including, if I judge by the way my renovation is going, a mediocre wannabe electrician and plumber. But for sure, one thing I'm not is a chemical engineer. So I'll do my best to speak about topics that I'm sure some of you will know much better than I will. So please feel free to contribute in the chat and have mercy on us non-scientists. Anyways, that having been said, the title of today's webinar, as Marta said, is Jet Fuel Quality, Tackling Non-CO2 Effects and Air Pollution. And I think because we wanted a lot of you to attend, we didn't want to put a too scary title. And the scary title would have mentioned the word aromatics. Okay, so aromatics. What are aromatics? It's not some kind of a dodgy perfume. It's one of the elements of jet fuel. They basically are molecules, hydrocarbon molecules, that have the specificity of having double links between carbon atoms, and when they combust, they produce soot. And I will explain why this matters. They are also useful at the moment for existing engines because they act as a component that maintains the O-rings swollen. But jet fuel standards specify that you need a minimum of 8% of aromatics to simplify, 8% of aromatics, when at the moment, if you look at jet fuel, how it is being produced in the world, the average aromatic content is a lot more between 16 and 20%. So to keep things very simple, the starting point of the work TNE is doing on this topic is that there's way more aromatics in the jet fuel than the one you need for the safe functioning of aircraft engines. Okay, so what's the issue? Why am I talking about this? What's the big deal? Well, not to spoil you the presentations of my esteemed colleagues afterwards, there's a number of issues with the aromatic content of jet fuel when it is too high. The first one is a climate problem. The soot particles that are being emitted by the engines create or are likely, let's say, to contribute to the formation of contrails. And I'm sure the very famous topic of non-CO2 doesn't need any further introduction nowadays, but these contrails act as a greenhouse gas. Okay, so basically aromatics, soot creates contrails. So if you reduce the aromatic level in fuel, you will also reduce contrails, and we'll let Jasper explain this a lot better than me. The second issue is surrounding air quality. Soot is not just about contrails, it's also the kind of thing that transforms into particulate matter, ultrafine particles, and the kind of thing that gets into your lungs when you live near airports. And this is a topic that Carlos will be talking about. If we reduce aromatics in jet fuel, we also improve air quality and therefore the health of citizens. And there is also a third issue, which is operational. If you use fuel with high aromatic content, you are also actually worsening the fuel flow, and you are actually therefore, as an airline, paying more than you should for the fuel because you have to put more in your tanks. And I think Jasper will also be mentioning this topic. Now, a lot of you are probably familiar with the fact that sustainable aviation fuels, which is one of the trendy topics at the moment in aviation, usually have no aromatics. So again, why are we talking about this today? Why do we not just let the work being done on SAF through Refuel EU and other topics? Well, that's a good question. But the thing is that for a long time, SAFs will be but the smallest part of the fuel being available to aviation. If you look at Refuel EU in 2030, you will have 5% of SAF and 95% of fossil fuel. So we are really looking at how can we reduce the aromatic content of the fossil fuel? How can we be pragmatic about the fact we still have a lot of fossil fuel around for the foreseeable future in aviation? So this event is also aimed at looking at how do we do it? How do we make it possible to reduce the aromatic content of fuel? And here we have three main topics. A technical topic. How does it work in the refining process, in the nitty-gritty of the refining? This is a topic that Niels will be talking about. Then, of course, how do we manage to do it from an energy point of view and therefore automatically from a cost point of view, the million-dollar question, right? This is what Giant will be talking about. And finally, since aviation, as you know, and thankfully is a heavily regulated sector because safety is the first and foremost priority, how do we manage this from a legal point of view, from a certification point of view, which is something that Carly will be talking about. So the aim of this event is to go a little bit deeper into the non-CO2 than the summit that we organized last year and that some of you may have attended, and to hear the science, thanks to all the speakers today, but also give an opportunity to people to ask questions, to participate to the debate, to brainstorm. We do not hold the pretense of having the truth. What we want is to create a platform for these important debates to take place. And this is what Transport and Environment's contribution to this issue wants to be. So I will let the event proceed now, and thank you all for joining and discussing how we can tap into this low-hanging fruit to reduce aviation climate impact and improve the health of everyone around airports. Thank you very much.
Thank you, Matteo. I would now like to introduce you to Jutta Paulus, Member of the European Parliament for the Greens EFA, who will give you the opening speech of this webinar. She has followed matters around the sustainability of aviation closely, working as Shadow Rapporteur for the Industry Research and Energy Committee on the Refuel EU aviation legislation. Therefore, she is well placed to break down the political state of play around jet fuel quality and the non-CO2 effects of aviation for us today. Thank you, Jutta.
Thank you very much. Thank you for first and foremost for organizing this event, but also for inviting me, of course. And I think it's really an underestimated issue, although it should have been on the plate for quite a long time. Some of you might remember 9/11, the event when the World Trade Center was attacked and then collapsed, and subsequently a flight ban was imposed over the United States. So for 3 days, all planes stayed aground. And as a consequence, the temperature, the nighttime temperature fell by 2 degrees Celsius, which is really remarkable. And I think this is a very, very valid proof that the non-CO2 effects of aviation are should have been known for quite a long time, and that we should have acted for even longer. Matteo has already lined out on the consequences of the additives to kerosene, or rather, let's say the ingredients of kerosene, where we have a lot of aromatics and also sulfur, which are mainly responsible for the non-CO2 effects of aviation. But they have been ignored for decades by policymakers. And now, as we are negotiating on the Fit for 55 package, which includes the RefuelEU aviation legislation, we are finally talking, at least we're talking about those non-CO2 effects, but unfortunately, we haven't been able to really address them already now. Right now, we are looking only at an MRV, so monitoring, reporting, and verification system in the ETS, and potentially a similar system for the RefuelEU aviation. Interestingly, the European Commission had commissioned a study at CE Delft for looking at the impact of those non-CO2 effects and also on mitigation. This study was commissioned in 2017. It took 4 years to complete, which is quite long actually. But after its completion in 2021, it was considered as classified and was not published. It was only published a year later, after the legislative proposal had been published already, and while we were in the midst of negotiations, and unfortunately we could not bring our colleagues in the European Parliament to take this up instantly in the regulation. So looking at how could we limit the content of aromatics in jet fuel in Europe, at least. Although already now the jet fuel standard says we have to have at least 8% of aromatics. So nowadays we're talking about 16%. So why not lower it to 8% right now? And so we cannot stop at MRV level. We need ambitious policies to follow up here. We know how to mitigate those CO2 effects. As I said, we can lower kerosene content, we can lower sulfur content. And the CE Delft study has some interesting figures on that, which says that in the regular jet A1, we have 17% of aromatics and a total sulfur content of 300 milligram per kilogram. And if we hydrotreat those fuels, meaning that we actually crack the aromatics to other compounds and lower the content of aromatics and of naphthalene, then of course the non-CO2 effects would also go down. And interestingly, CE Delft says that the benefit for society would actually be positive, because you have lower air pollution, you have lower greenhouse gas emissions, you have lower emissions from and also on the ground, of course, and we have much lower health costs. And the change in consumer surplus is really negligible, so to speak. It only makes a minuscule part of the cost of aviation as a whole, which, as we all know, is subsidized anyway, because we're not counting in the external costs such as health effects, pollution effects, and of course, climate change. Matteo has already spoken about the sustainable aviation fuels, which we are aiming to bring to life, so to speak, in the RefuelEU aviation. The figures that the Commission has proposed are fairly low. We are still trying to raise them also right now in the negotiations at trilogue level. And we are also trying to limit the exemptions which some member states want to put in there, so that really all airports should be subject to this regulation and having to offer those sustainable aviation fuels. On the long term, we have to go further than just switching to more or less, let's call them sustainable biofuels. We will have to switch to synthetical aviation fuels for the simple reason that the land mass on this planet is limited. So we will never be able to grow all these biofuels, which would also need for shipping, of course, because you will never be able to run to sail from Shanghai to Rotterdam on batteries. So of course there we will also need fuels which you can actually burn, and they're the only way forward. The only way to the future is of course synthetical fuels, and it needs aviation to kick that off, because if I may say so, aviation is a sector where the cost effects are not so large as in other sectors. And so why should it be the EU? Well, actually, first and foremost, the EU is the front runner on historical emissions for climate change, but it's also the front runner on environmental and climate legislation. And this should not stop at the more simple things such as energy and industry, but we also have to tackle aviation and shipping. And therefore, it is the EU that should set standards here and should not, as it did when the EU first tried to include aviation in the emissions trading scheme, back down again when the big flight companies are trying to threaten that they will not fly to Europe ever again. I don't think that this will ever happen, because the market is simply too large for that. On the short term, of course, the cost will be higher, but when the technology kicks off, then we are entering the cost regression curve, as we have seen already in the renewable energy. And therefore, it is time now to set the goalposts for the year 2030 in order for industry to be ready to provide the necessary volumes. And I'm really glad that we're talking about including standards for kerosene here, and I still hope that we might be able to achieve more than we are set on right now in the negotiations. And I also need the help of you all to talk to your MEPs and to your political parties, to your member states, and showing that this is an issue which should not be left off the shelf any longer. Thank you very much.
Thank you, Jutta. Now, for the next section of the webinar, we have two presentations of preliminary findings on the climate and social benefits of hydrotreating jet fuel, followed by a Q&A. The first presentation will be by Jasper Faber, Mobility and Transport Manager at CE Delft. He is an expert in the field of policies to address the non-CO2 climate impacts of aviation. I will today present the study he led on the social cost benefits analysis of jet fuel hydrotreatment. Please feel free to start sending questions now for the Q&A that will follow both presentations. The floor is yours, Jasper.
Thank you, Marta. And thank you, TNE, for organizing this event. I want to give you a quick presentation on a study we did on the social costs and benefits of advanced aviation fuels. And before I start with my presentation, I must thank Eric Lombard, who I saw is also present, for reviewing our first report on this topic and spotting a few mistakes in our calculations, which we corrected in a corrigendum that's on our website. And we took the opportunity also to include newer findings on the environmental impact or the climate impact of contrails and sulfur emissions, which helped us to update the findings. Let me go to the next slide. This is a short introduction of CE Delft. And in the view of the time, I will skip this and first present you an overview of the the study we did, and then the next slide is the results, and that's it from me. So in the context of a Horizon 2020 project called JetScreen, we have been asked by Airbus to analyze the social costs and benefits of using hydrotreated fuels. Within the JetScreen project, 3 types of hydrotreated Jet A1 were produced, called HT1, HT2, HT3, with lower total aromatics, lower naphthalene, and lower sulfur concentrations than the reference fuel. In this presentation, I'll only focus on HT2. In the report that is on our website, you can also find the details of others. And you'll note that HT2 has slightly lower total aromatics than the reference fuel, so 16% instead of 17%. Has here something is going wrong. Significantly lower naphthalenes. So instead of 1.8% by volume, it has almost nothing. It should be 0.2 instead of 6.2, I think. And also almost complete reduction of sulfur. What we did for HT2 and also for the other fuels is identify all the impacts, the economic, environmental, and social impacts, and express them in monetary terms. For the direct effects, which are directly related to the production and the use of alternative fuels, we estimated how much it would cost to hydrotreat jet fuel, what the change in fuel cost would be, and what the change in maintenance and retrofit costs for aircraft would be. Then the indirect effects, the effects not on the aviation sector itself, but on the market it serves. We looked at the change in consumer surplus because the fuel cost increase, so tickets get slightly more expensive, so there are fewer people who can fly, and this changes the consumer surplus. And then there's also the external effects, which are the change in air pollutant emissions, change in greenhouse gas emissions, and also the change in the climate impact, and the change in emissions from fuel production. And on the next slide, I present the findings. So the direct effects, using 2018 fuel and gas prices, we estimated, and assuming that the hydrogen, which would be required to hydrotreat the jet fuel, would be produced from natural gas, which is the main or the dominant way to produce hydrogen, at least in Europe. We estimated that the production cost would be a little bit over 300 million euros per year to hydrotreat all jet fuel used globally. Because the hydrotreating means that the energy content of the fuel increases, you also save fuel, and this amounts to almost 500 million euros per year. We weren't able to quantify the additional maintenance and potentially retrofit costs, which is not really relevant for HT2, but there's HT3, which has aromatics content lower than 8%, which could result in some need for retrofits. Ticket prices would increase by 4% of 1%, and this would lead to a reduction in the consumer surplus of 100,000 euros on a global scale. The air pollution impacts would be that because of lower SO2 and PM emissions during landing and takeoff, the health costs would globally reduce by 85 million euros. Because of lower fuel use, the aviation CO2 would also reduce by about 250 million tons. But bear in mind that on the other side of the equation, because the fuel has to be hydrotreated and the hydrogen is produced from natural gas, there are higher CO2 emissions during the production of the fuels. I'll come to that later. Low sulfur fuels result in lower emissions of sulfur particles, sulfate particles, which reflect the sunlight. And when you emit less of those particles, it actually means that more sunlight reaches the surface of the Earth, which has a warming effect. And we quantify this at 8,500 million euros. But there's also a climate benefit, which actually exceeds the impact of sulfate particles by far, which is that there will be fewer contrails produced. When there are fewer PM emissions, there are fewer particles in the upper atmosphere, which act as a condensation nucleus for the formation of contrails. So there will be fewer contrails. And we estimate this benefit at 19,000 million euros per year globally. But I also put an asterisk here because this actually is the least certain, or the estimate that has the highest degree of uncertainty. So it would merit further analysis whether this figure is actually right. And then, as I said, there will also be CO2 emissions during the production of the fuels, and especially during the production of the hydrogen to hydrotreated fuels. And these amount to almost 500 million euros annually. If we then add up all the costs and all the benefits, we find a benefit of 10,000 million euros, a little bit more. The benefit by which the benefits of using this hydrotreated fuel exceed the cost. In this example, this is an annual benefit, mainly a climate benefit, as you can see, but also an air pollution benefit that can be gained from using this type of hydrotreated fuel. There is more information on our website. You'll find a link in the presentation. You can also Google social cost and benefits of advanced aviation fuels, where there's both the old report and the updated version of the cost-benefit analysis, which addressed some of the issues that Eric Rombard raised, and also updated the estimates of climate impacts. And there you can also find the information on the other hydrotreated fuels and how they compare. Just suffice to say at this moment that all the three types of hydrotreated fuels we analyzed in this report showed that the benefits of the social benefits of using them exceeded the cost by a considerable margin. And that's the end of my presentation. Thank you.
Thank you, Jasper. We'll have a Q&A with both Jasper and Carlos after Carlos's presentation. But I'd now like to introduce you to Carlos López de la Osa, Technical Manager in the Aviation team at Transport and Environment, who leads our work on the non-CO2 effects of aviation. He will be presenting the preliminary findings of a study which looks at the long-neglected negative health impacts of poor fuel quality. Thank you, Carlos.
Thank you very much, Marta. And thank you everyone for attending this session. Let me just click on share screen with you. Here we are. So yeah, I'd like to speak for a few minutes about the air quality impact of aviation, which is an important problem, yet something which has been probably historically a bit neglected, but which can also be mitigated with higher quality fuel. So when we think about air quality issues, we tend to think about industry, about road transport, but the truth is that when we look at the amount of particulate matter emissions around the world, aviation is responsible for around 3 to 4% of global emission, which is comparable to the contribution of road transport. And out of those particle emissions, 14% of them happen at or near ground during the landing and takeoff cycle. So we have two problems caused by the same thing. So high in the air, we have the particle emissions which drive the formation of contrails. Down in the ground, the same emissions drive poor air quality. Now, when we talk about emissions of aircraft engines, there are a huge amount of species being emitted, both particle matters. Within the particle matters, we have soot and black carbon, and then we have a number of gases as well, such as nitrous oxides, carbon monoxides, and sulfur dioxide. Here, I would like to focus on two of those types. So first, non-volatile particulate matter, also referred to as soot, which is essentially black carbon, product of the incomplete combustion of the hydrocarbons in the jet engines, plus some impurities. And we have already discussed that those emissions are driven largely by aromatics and naphthalene. And second, I'd like us to focus on volatile particulate matter emissions, which are essentially liquid droplets formed from the condensation of gas emissions. And these are partly driven by sulfur emissions coming from the jet engine. And in this case, the amount of sulfur emitted by the jet engine is directly related to the amount of sulfur in the jet fuel. So we've discussed that during the ground section of a flight, this is where the air quality impact will happen. And we can think of impact around airports, but also beyond. So on the right-hand side, you can see a map of the Los Angeles airport and how the particulate matter emission affect even 10, 15 kilometers downwind from the airport, rising significantly the amount of background particles by a factor of up to 4 and 6 times more. And also another study in 4 European cities found that you could find particulate matters which could be traced to aircraft emissions in the city center. That's true for London, Barcelona, Zurich, or Helsinki. So at the end of the day, this is, although we tend to think of road traffic as a big driver of air pollution, we actually see that in the vicinity of airports up to 20 kilometers, we have this problem, and we cannot neglect that we have more than 33 million people living within a 20 kilometer radius of the top 20 European airports alone. So only looking at those with the most traffic, but of course, many European cities do have airports. So the total number of European population will be even larger. Now, when it comes to measuring this problem, there's another challenge, and it's due to the fact that the emissions from aircraft are really small. When we see the size, the average size of the particulate matters emitted by aircraft engine, they are smaller than any other source, like industry, road transport. And here we see that we have the traditional air quality measurements are the mass of particles of 10 micrometers in diameter and 2.5 micrometers in diameter. Now, the average size of particulate matters from aircraft is around 25 nanometers. That is 100 times smaller than the smaller part of what we measure today. And what does it happen when we try to weigh it? We find that one single particle of 2.5 micrometers has the same weight as 1 million particles of 25 nanometers, assuming they're made of the same substance. But there are caveats to this. So they're not like for like, because on the one hand, we have one particle, on the other, we have 1 million. The 1 million particles have a combined 100 times more surface. So it's not about mass. Surface also matters because the interaction of the pollutants with the cells of the body are through the surface. And more importantly, the smaller the particle, the worse it is for health, because they get deeper in the body and they stay for longer. Whereas bigger particles above 10 micrometers are captured in the upper respiratory tract. Particles below 100 nanometers, and most aviation emissions fall within this range, get into the bloodstream. So that means they can get deeper in the body than other sources of emission. What is the effect that all this has on the health? Well, let's look at the findings of one of the most thorough studies that have been conducted so far. It's a very recent study of the health impact of the population around the Schiphol airport. And researchers found that there is an increased risk of high blood pressure, heart attack, diabetes, and birth defects. So there was a clear relationship between those causes and the amount of air traffic around Schiphol. And another important finding that we need to take into account is that we've seen before all the drivers of different gases and particles, but black carbon is the main driver of health impact. It's the one that correlates best with the health impact of aviation emission. So we are in this event, and I'm talking about this because obviously we can present hydrotreated fuels as a solution for this problem. Why? Because hydrotreated fuels come with first a reduction in sulfur, which drives fewer volatile particle matter emission, and also a reduction in naphthalene and monoaromatics, which reduce the soot and black carbon emissions. And this is not a new topic. This has been studied for quite some time, although maybe it hasn't been so prominent. But EASA conducted a study back in 2010 on the possibility to remove sulfur or reduce sulfur in aviation fuel. And it came to the conclusion that if sulfur was to be reduced from jet fuel used in Europe, we will be saving around 130 to 430 million per year on healthcare expenditure. And also these results may be underestimated because we are quantifying the benefits in terms of mass, and we're not taking into account the number of particles, as we've seen before. If these were the findings, why didn't we do anything? Because there were still questions on the climate impact of hydrotreated fuels. Back in 2010, the impact of soot emissions, it was still unknown. How could they drive the climate warming or cooling? What was their effect on contrails? But we can say that since 2010, the progress that we've had in scientific research has clarified many of the open points which existed back in 2010. So as a conclusion, we have accumulating evidence on the climate benefit of hydrotreating jet fuel, but also more and more studies, as we have seen, are highlighting the air quality and health impacts of current jet fuel. So we have an additional reason to hydrotreat fuel. The scientific community accepts as well that the impact of ultrafine particles is serious because they are smaller, therefore they can get deeper into the body. And then as next steps, Europe would need to take ambitious action to first mandate hydrotreating jet fuel as a standard. And secondly, also improving the air quality directive in order to ensure that ultrafine particle emissions are properly measured and limited, something which is not the case today and which we need in order to quantify the problem and to be able to solve it more effectively. Let me end by saying that there is no safe level of air pollution. So any step we can take to reduce air pollution will always be welcome and will always have benefit, no trade-offs. It will only be good. So thank you very much.
Thank you, Carlos. We'll now move to 10 minutes of questions. Please feel free to keep sending questions. The first one comes from Guillermo, and I think this is for either Jasper or Carlos to answer. Are NOx emissions from HD2 higher and are contrails totally avoided?
Can you repeat quickly? Sorry.
So this is the question from Guillermo, so you can see it in the chat. Are NOx emissions from HD2 higher and are contrails totally avoided?
Well, I'm not sure about NOx emissions. I'm also not sure that the temperature in the combustion chamber would increase necessarily, even though the lower heating value of the fuel would increase, but you would use less fuel. But I'm not an engine engineer, so I don't know, and we didn't look into NOx emissions. In the jet stream project, there was no assumption that NOx emissions would change as a result of using hydrotreated fuels, as far as I'm aware. With regards to contrails, no, contrails will not completely be avoided. There are different ways in which contrails come into being, and nucleation of ice on particulate emissions is only one of them. That can be reduced to some extent, but other ways of contrail emergence will still remain. But the contrails, contrail-induced cirrus, and also the longevity of contrails can be significantly reduced.
Yeah, if I may add very quickly, it's true that the higher hydrogen content of the fuels would drive a higher water formation and in the exhaust, but the effect of that is quite small, because in the formation of contrails, they happen in ice supersaturated regions. That means that most of the water that will condense to form the contrails is already existing in the atmosphere. So even if we have a tiny more amount of hydrogen, therefore water being emitted by the aircraft engine, it will not have a significant impact in terms of more contrails.
Okay, thank you. So the next question is for Jasper. Have you done a sensitivity analysis on the financial benefits of hydrotreated fuels? The fact that there is a cost benefit, even without the emissions benefit, provides great commercial impetus. Right, is the question.
Yeah, so the commercial impetus would be from the airlines if they could buy a fuel that has a higher energy content. They would be very happy to do so. In practice, though, there is no differentiation in the fuel that is offered. So if a refinery would hydrotreat fuel, there's no way an airline would know it, and there's no way an airline could take that into account. So I don't think that the market will function in this way.
Okay, then a question from Magnus. If regular aviation fuel has to contain 8% aromatics in order for the engine to work, how can SAF with no aromatic content work?
Yeah, maybe I can take that one. At the moment, they're having also other questions in the chat around the 8% limit. So it is true that existing fossil jet A fuel standard doesn't have a minimum aromatic content, but now the biofuels, well, the SAF standard does contain the minimum 8%. And the reason is that in jet fuel, in fossil jet fuel, like no one thought about having an aromatic content below 8%. But now with the zero aromatic SAFs around, so very soon to come, people started to ask, are there any effects of low aromatics? And this is where we got to the conclusion that actually zero aromatics may not be fully compatible with existing aircraft technology. That's where the 8% came from. How can we try to move towards 100% SAF, 0% aromatics? Because aircraft manufacturers, engine manufacturers are currently doing the work to test and finally certify all the aircraft system and engine systems to be able to operate with 0% aromatics. So the seal swells, the O-rings, all the lubricity and freezing points, all the properties are currently being assessed so that in the near future, we will be able to fly with 100% SAF or with 100% hydrotreated fuel that will contain 0% aromatics. And in terms of time frame, the large manufacturers have committed to achieving so by 2030.
Thank you, Carlos. I have a question for Jasper. If the world wanted to transition all of its Jet A1 to be hydrotreated, what kind of infrastructure development would be required, and how many years could it take to make it a reality?
That's an interesting question and very hard to answer. It depends on, I think, two things. First of all, the hydrogen generation capacity, and second, the hydrotreatment capacity in refineries. In the context of desulfurizing marine fuels, we did a study 5 years ago on hydrotreatment capacity in refineries and found that at least at that time there was a significant oversupply of hydrotreatment capacity in refineries worldwide, and we then predicted that it would not be a problem to desulfurize all the marine fuels. And in fact, when that came into being in 2020, there was hardly a noticeable change in price or an effect on the oil market. So I think our analysis at that point in time was pretty correct. I don't know what the situation is now. I would assume that there's still overcapacity in hydrotreatment. With regards to production of hydrogen, if you are content with using gray hydrogen, so hydrogen produced from natural gas, I think there's no shortage of capacity of producing it. If you would, which would be better for the climate, of course, use green hydrogen, hydrogen produced from renewable fuels by electrolysis of water. I think there is, it might take a decade or so before we can produce sufficient quantities that also take into account demands from other sectors for green hydrogen.
Thank you. And perhaps one final question from Dimitar. What would the relevance to know exactly the amount of contrails that are prevented when it comes to hydrotreated fuels? And if this is indeed of high relevance, what would be the research needed and associated timeline?
So we have already a good body of research when it comes to reducing the amount of particles through higher quality fuel. It is true that a part of those fuels have been sustainable aviation fuels, whereas others have been hydrotreated fuels. But in general, we already have a good knowledge of the issue. And with what we know already, this is a route that we should pursue. I'd say that further research could be desirable in case we wanted to, say, pinpoint the exact sort of extent of the solution. And in terms of timeline, at the end of the day, this research has been done already in projects such as ECLIF, and I'm pretty sure that institutions such as the DLR have good knowledge to assemble this type of test methodology and to be able to quickly bring useful results.
Okay, thank you for all of your questions. Many of your questions will actually hopefully be covered in the second part of the webinar, which will be a roundtable discussion in which we'll look at the industrial, economic and legal feasibility of hydrotreating jet fuel. We have 3 fantastic panelists with us today. Firstly, we have Niels Beck, Director of Business Development at Kalundborg Refinery, the largest oil refinery in Denmark, who will be able to tell us about the industrial side of hydrotreating jet fuel. Our second panelist is Jayant Mukhopadhyay, the aviation researcher at the International Council on Clean Transportation, or the ICCT. The ICCT have been working on a new study on the cost impact of hydrotreating jet fuel, which will provide a valuable contribution to the panel. Finally, we have Carly Hicks, Legal Director at Opportunity Green, an NGO that aims to find innovative legal pathways for climate action, including on jet fuel policy. Panelists, please keep your answers to around 2 to 3 minutes so we can stick within the time schedule. And we'll have an opportunity for Q&A towards the end of the webinar. So Niels, I would like to start with you, to start the discussion with you. Could you give a brief overview of how hydrotreating jet fuel works and how it can help reduce sulfur, naphthalene, and aromatics?
Sure, and thank you for having me today. So I will not go into the technical details. I don't think it's necessary here. But basically, we can view hydrotreating as a black box where we add heat, we add hydrogen, and we add a catalyst. And by doing so, we can achieve to reduce sulfur, nitrogen, oxygen, and aromats in the fuel. So basically, these reactions have proceed in an order. And what happens first here is we saturate the linear hydrocarbons. After that, we proceed to removing the sulfur, the nitrogen, and then lastly the aromats. What determines this is basically the amount of hydrogen we use, the temperature in which we do this, the pressure, and the catalytic activity. So you can say we can tailor the units to achieve the amount of hydrotreating we want and what is necessary, because as others have already pointed out, the more we hydrotreat, the more hydrogen we use, and that has also some negative consequences for climate and using scarce resources, as is the thing right now in Europe.
Thank you for that, Niels. So now moving on to the economic side, the economic feasibility of this process. Jayant, what were the ICCT's findings on the cost impact of hydrotreating jet fuel? And did you assess other technologies to reduce aromatics and naphthalene from jet fuel?
Hi. So we looked at costs of two methods, both hydrotreating and extractive distillation. You've heard about hydrotreating already. Extractive distillation is a slightly more precise method, giving you like more granular control over the removal of naphthalenes and aromatics. It's common practice in pharmaceuticals and petrochemical industries, however, not too common in refineries. And it would require the development of some new technology in that sense. Now, hydrotreating, as you just heard, is fairly common practice in refineries, especially bigger conversion refineries. And yes, you are able to remove undesirable elements like sulfur, nitrogen, which you can't really do with extractive distillation. I'll focus on the costs of hydrotreating for this bit, and you'll see that these costs differ slightly from those presented by Jasper earlier, because we didn't consider the increase in the specific energy of jet fuel, which would then reduce the jet fuel consumption. So the price premium we found hovers around 3 to 8 cents per liter of jet fuel, depending on the size of the refinery. And that's about a 5% increase in jet fuel cost. But that doesn't really mean much to most people. So translating it into a ticket price change is a little more useful. So for that, if you're traveling from Berlin to Paris, which you can take a train for, costs usually less than 50 euros. And the price increase would be around €1, which is really a fairly perceptible change if you just look at variation by carrier or by calendar day for that matter. Now, it said if you're flying across the Atlantic from Paris to New York, the price would increase by about 5 to 10 euros per flight ticket. That's usually in the 500 to 750 euro range. And that's roughly 1% or less than 1% increase in both cases for short and long haul flights.
Thank you for that, Jayant. So now, Carly, we've heard about how this process works and the economic feasibility, but what does the new Fit 55 package from the EU bring to the table in terms of improving jet fuel quality?
Yeah, so as Jutta mentioned earlier, Refuel EU in particular intends to reduce the climate impact of aviation primarily by incentivizing or mandating rather the use of SAFs. But as we know, and given that SAFs contain little to no aromatics, as we've been discussing on this webinar already, this will have a huge effect on increasing jet fuel quality and decreasing the non-CO2 effects of aviation. Unfortunately, even if we get to 85% use of SAFs in 2050, which is what I believe the European Parliament position currently is, that still leaves the 15% of non-SAFs. And it also means that progress on scaling up SAFs is relatively slow. The climate crisis means that we can't wait until 2050 to see an improvement in jet fuel quality standards. So the real advantage of Refuel EU as it is at the moment is to monitor the jet fuel that we're using in airplanes. And we've also had some discussion already on whether actually we use 8%, whether we use 16% sort of aromatic content in jet fuel. And we probably need a little bit more information on that. And that's where the monitoring, the reporting, verification requirements in Refuel EU is so important. So we'll just get a better idea of what we're using at the moment. Aircraft operators and fuel suppliers will be required to report on a yearly basis to the EASA on things like the conversion technology used in their fuel stocks, characteristics of the feedstocks that are used for production, life cycle emissions. And the EASA in turn will report to the Commission once a year on compliance of operators and fuel suppliers, and also kind of just more generally on the status of the European fuels market. At the same time, under the EU ETS, which has been agreed in trialogue, they've set up a pilot scheme monitoring the non-CO2 effects of each flight. Of course, all this is great, but what we need to see is more happening in the future, and that's where, that's going to be the change that we see. Refuel EU and the current Fit 55 package is a great start.
Thank you, Carly. So Niels, to come back to the industrial the angle, we know that hydrotreating practices are common in road diesel and gasoline. Can you tell us something more about how these processes are used today and what it would take to apply it to kerosene?
Yeah, sure. At the Kalundborg refinery today, we are already producing a Swedish quality diesel called MK1 or city diesel. This is characterized with having an amount of aromats less than 5 ppm. So a very low number. Sulfur is also way down, probably around 1 ppm, at least below 5 ppm. So I think this is probably the golden standard, and of course one we cannot apply directly to air transportation due to the requirements of having the 8% aromats, as we already discussed. But it also means that setting up a goal of hydrotreating jet fuel is not unrealistic. Sweden set up this goal to introduce the city diesel, I believe back in the late 90s or early 2000s. And it was achieved. So giving that you have sufficient time to implement this in the refineries, it can certainly be done.
Thank you. So this question came up in the chat earlier, Jayant, about sustainable aviation fuels and them also being a solution for non-CO2 effects. So can you put this in perspective for us on how hydrotreated fuels compare to sustainable aviation fuels in terms of both cost and the hydrogen needs?
Yes, and so also following up from the question that was asked earlier in the chat, was SAF and sustainable aviation fuel can mean a number of things. Biofuels from various feedstock, or even synthetic fuel made by combining carbon and hydrogen to create the jet fuel. And cost estimates for these vary considerably by feedstock, geography, and sort of the financial assumptions used. A decent rule of thumb is that low life cycle emission biofuels come at a price premium of 50% to over 200% over jet fuel. These are back of the envelope ballpark figures, so don't quote me on those, but which would roughly translate to something between a 15% to 30% increase in ticket prices, or €7 for the Paris to Berlin, and 100 euros for Paris to New York. Now, these costs for biofuels aren't really expected to decline much, as a large fraction of the cost of producing the biofuel is the feedstock itself. And so improvements in technology will only reduce the cost a little bit. Synthetic jet fuel, on the other hand, is on the order of 3 to 4 times as expensive as jet fuel. And although this is also expected to decline over the coming years as the technology matures, efficiencies are improved, and sort of the economies of scale are exploited, it is still quite a lot more expensive. And this will nearly double the cost of your flight ticket, either both on short haul and the long haul flight segments. So that using just synthetic jet fuel would be a significant price increase. And you compare this to the earlier ticket price increase of about 1% for when you use hydrotreated jet fuel. But I'm also wary of comparing hydrotreated jet fuel to the cost of using SAF, because using SAF would reduce greenhouse gas emissions on a life cycle basis, while also reducing the impact of non-CO2 effects. Hydrotreating would not address the greenhouse gas emissions in any meaningful way, and would only reduce the non-CO2 effect.
Thank you, Jayant. So finally, from Carly, what are the future legal options that Europe has to set higher jet fuel quality standards?
Yeah, so in short, there are lots. As I alluded to earlier, the biggest advantage of the MRV in the Refuel EU is that it gives us a baseline for future regulation of non-CO2 effects of aviation. At the moment, we know there's no incentive for refineries to, whether financially or legally, to modify production processes to reduce the content of aromatics, sulfur or naphthalene in conventional jet fuel. And we also know that airlines aren't going to voluntarily pay for more expensive jet fuel. So what we actually need to see is regulation that mandates, for example, a gradual reduction in the upper limit of aromatics and jet fuel on the basis of the information that we gather in the MRV in Refuel EU. And that will provide obviously the incentive for investment, and the knock-on effect being significant economic advantages for European businesses that make these changes. We've also seen quite recently that the European Commission have sort of moved to put in place a pilot project for a European body for jet fuel standards. And that's quite interesting, because at the moment, jet fuel standards, as we've been discussing a little bit in the seminar already, are primarily set by an American organisation. It's a private organisation that, among other things, mandates the jet fuel A1 standard. The EU, via the EASA and kind of member state governments, has a place on this commission, but it doesn't have kind of a more important place than other organisations, industry bodies, for example. Progress is really slow on the ASTM because it's not kind of incentivised by any environmental objectives at all, and it doesn't have formal recognition in EU law at the moment. So the idea of setting up this European body to do essentially a similar thing to what the ASTM does is a really interesting one, because it means that the Commission could essentially mandate that European body sets jet fuel standards in accordance with EU law, EU climate law in particular, and that jet fuel standards are therefore reflective of EU environmental priorities. There's no reason why the EU can't do this. It's entitled to do this under Article 191 and 192 TFEU on environmental protection. The other advantage of this option is that it can be done quite quickly once we've kind of got a baseline of information under the MRV in the Refuel EU. There's no need, for example, to wait for political debate over what a multiplier of the EU ETS might be for non-CO2 effects, if we were thinking of adding it into the EU ETS, which is also another option that we could pursue. So yeah, there's a number of things that we can go after. The EU ETS potentially, this European body, which I think is really interesting, and kind of a sliding scale of reducing aromatics and jet fuel. I think the message really though is that it's not illegal barriers that are going to be the issue. It's once the technical issues are worked out, the legals can probably just follow on from that. The second point is that we can't rely on SAF scaling up because progress on that is going to be too slow, and there are things that we can do now. And I think the third is that unless the EU acts on this in a mandatory way, we know that there's not going to be the progress that we need. So regulation is really important.
Thank you for that, Carly. So we now still have roughly 10-15 minutes left for questions. So please feel free to send more to the chat. The first one that I think will be very interesting to answer is from Alba. She asks, why should we incentivize refiners to invest more in fossil jet hydrotreating instead of incentivizing them to invest much more in SAF to deploy SAF volumes faster? I don't know if which one of you would like to take that question. Yes, Niels.
I think this relates to another comment I saw in the chat forum, and that was how much hydrogen would we need to hydrotreat the fossil fuels compared to how much hydrogen would be needed in order to produce the synthetic fuels. And I think this answer, the one answers the other, because if we were to build up the molecules from CO2 and renewable hydrogen, these fuels contain around 10% hydrogen, so that is what is needed. Whereas if we're going to remove aromats, which are present in a few percent, then we only need a fraction of the hydrogen in order to achieve a lot on the climate side. And as the situation is in Europe right now, the situation is more or less that with the current situation with Russian gas, with the war in Ukraine and so on, the price for electricity is just very high. So nobody in their right mind at this moment would spend electricity to produce hydrogen when at the same time the consumers are struggling to get electricity at a reasonable price. So I just don't think it's realistic to take the full steps at this time. Whereas it makes a lot of sense to implement something which you can do rather quickly, and then at the same time it's not wasted. We can still use these resources when we get to the day where we will have enough electricity to produce the full synthetic fuels with all the benefits they have.
Jasper, you'd like to jump in here as well?
Yes, and first echo what Niels has said. I agree with his answer. I also wanted to bring in another perspective, and that is that under the Renewable Energy Directive 3, which we haven't discussed here today, there is a minimum amount of renewable fuels of non-biological origin, or RFNBOs, that need to be used in the transport sector. And one type of fuel that classifies as an RFNBO is a hydrotreated fossil fuel. If you use green hydrogen, that is. And I don't know all the rules, so it may not classify completely, but only as a percentage. But I think if you're going to hydrotreat fuel, it makes, because you have to under the Renewable Energy Directive, it makes more sense to hydrotreat jet fuel, where you have the additional climate benefit of having fewer contrails, than to hydrotreat road fuels where you don't have this additional benefit.
Thank you for that contribution, Jasper. I have a question for Carly. So new engines will likely require 0% aromatics. How would 8% de-aromatized fuel and 0% aromatic fuel work together? Would you need two separate standards?
I don't know. I'm not a technical expert on kind of fuel standards. I don't think you would need two separate standards, because I don't know the answer to that. I don't think that you would need two separate fuel standards. I guess that would be something that this European body could look at in the first instance, but my kind of off the cuff thought would be no, you wouldn't. I would say that fuel certification can be worked out in a number of ways, and that is something that we need to think about as we kind of move through this process of regulating non-CO2, but and who you put the requirement on. But I don't believe that you would need two separate standards. You would just need to account for those eventualities in the standard that you measured.
Yeah, Jayan, I saw you answered this question in the chat earlier, but I thought it would be interesting to bring it to the discussion as well. Jonas asked, given that a small part of flights are responsible for 80% of contrails, can we find a way to optimize the use of hydrotreated fuel?
I think this is a really interesting question because it should be done. Like there are places where you can have a higher impact by prioritizing low aromatic, low naphthalene content fuels to those flights that are responsible for a greater chunk of the contrail formation. There's a couple of difficulties, challenges in that. First being that the availability of these fuels will likely be fairly limited geographically, and will likely be used wherever closest, instead of having them shipped out to flights that would benefit from the low aromatic content. And the second thing is persistent contrail formation prediction is still quite tricky, especially doing it in advance of flight is particularly difficult. These weather conditions in high contrail probability areas change quickly and without any further like future notice. So it's difficult to really quantify which flights a priori quantify which flights to be prioritizing for these fuels. I see Jasper has his hand up.
Okay, yeah, Jasper, you can add an extra contribution.
Yeah, and also in response to a question from Matt in the chat, what would persuade airlines to buy hydrotreated jet fuel? I agree with Jayan that, of course, if I knew a certain flight would go through a ice supersaturated area and I have a limited amount of hydrotreated jet fuel, you should bring it to that plane. But the practicalities of that are enormous. It's not like an aircraft goes to an airport and orders a batch of fuel. Those airports have general, at least the larger airports, have common fuel tanks where all the fuels from different suppliers are commingled and then supplied as a mix to the aircraft. So there's no direct link between the fuel producer and the airline or the aircraft, and it would be very hard to bypass that, and it would also entail very high costs and operations to bypass that. So ideally, it would be a very good way to use the limited amount of hydrotreated jet fuel that we might have, but it will be very impracticable to do so.
Yeah, and maybe I can now ask Niels the question from Matt in the chat. So what would persuade airlines to buy hydrotreated jet fuel?
I don't think there's a lot of things that would persuade them. I guess the most effective thing you have here is legislation that they would need to buy it. I don't really see the benefit for them.
Okay, maybe I can now ask a question to Carly as well, more on this, on the legislative side. So what would the cost of certifying every aircraft type in the world what would be the cost of certifying every aircraft type in the world if the EU were to come up with a new jet fuel specification? Aircraft can only fly on fuels that they are certified to use. Or maybe that Giant could also have a comment on that question.
I mean, in terms of cost, I'm not the best case to answer that, I would say. I think the issue here is whether you accept the fact that the EU is in homage to existing fuel standards or not. I think if you accept that the EU has a priority on climate change, and there are tools available to it to reduce the non-CO2 impacts of aviation, and you accept the fact that the EU has the competence to regulate on that, which it does, then you've got the possibility to introduce EU-based fuel standards. The question of whether, the EU doesn't have to set up its own fuel body, it doesn't have to set up its own fuel standards, but that means that we are beholden to existing fuel standards and the rate of change in those standards, which we know are likely not to change as quickly as we would like to see it happen. There's no technical reason why an aircraft can't be certified to meet 2 fuel standards. Obviously, that will have an administrative cost to airlines and to fuel suppliers and whoever else is responsible for the certification, but there's no reason why that can't happen. And I guess the other point is that if the EU does move forward to put its own fuel standards in place, the size of the EU market means that it's likely that other fuel standards such as the ASTM and DEF will follow suit. And as I think somebody's already put in the chat, I'm not aware, but apparently those standards organisations are already working vigorously on that. So, we'd hope that would follow on from the EU being at the forefront of these changes.
Carlos, would you like to add something to that?
Yeah, so I fully agree with what Carly has just said. And indeed, the cost of certifying aircraft to a new fuel standard, they shouldn't be huge if things are done right. So we wouldn't be starting from scratch, and we will be removing some elements from jet fuel or reducing them, but within known territory. So we're not completely changing the composition of jet fuel. It will still remain pretty much the same. We're just reducing a certain amount of compounds, but we wouldn't be starting from a place in which we need to carry out a massive amount of, say, flight tests, lab tests, and things like that. So we will be in quite known territory. And personally, I will to kind of see more on from an AMI point of view, that is where a lot of the effort would lay.
Thank you for adding that, Carlos. Yeah, maybe one final question, and any one of you can pick this up if you want to. What would be your message to regulators and airlines on low aromatic fuels?
if I may just very quickly, we have already a very good body of research and knowledge. And for sure, there are some things that we still need to fine tune or to get a better understanding on. But where we are today, with what we know today of the climate crisis, of the health impacts of aviation, the precautionary principle should move us to act even faster than what we have done now. And if there are remaining questions, those can be solved pretty quickly if we get our act together and we assemble, a good research funding in the next 1-2 years.
And Jasper as well. Carly, you go first.
Sorry, I was just going to say I agree with that. I was just going to say that we know that unless the EU regulators act to put in place mandatory obligations, not a lot is going to happen. We cannot rely on scaling up SAF production because nothing will happen quickly enough. We need to act now. And as Matteo started out by saying at the top of this seminar, regulating on non-CO2 emissions is low-hanging fruit. As Carlos has just said, we've got the information. We can do this relatively quickly, and we should do it.
And Jasper?
Yeah, I think I'm in complete agreement with two previous speakers. In my view, the evidence is sufficient to start drafting and discussing regulation, and we should not engage in another round of more basic research, because the evidence that we have combined with the precautionary principles should be sufficient reason to start regulating this.
And Anise, do you have anything you'd like to add?
I can only echo what has been said. Don't really have anything else to contribute. It's a good idea, and should explore it.
I would like to add that the regulators should see this from a practical point of view. As Jasper has already mentioned, there's a limited amount of fuel delivery systems available. There's one tanks in airports, more or less. So it needs to be implemented in a practical way, and not the mess that we sometimes see from the EU, which is really standing in the way for us people closer to reality to act out what was intended. So the more practical we keep it, the faster we can act.
Great. I think we'll leave it there for the roundtable discussion. Thank you to all of our participants for your thoughtful questions and speakers for your valuable insights. Over the last hour and a half, we've been able to highlight the clear climate, social, and health benefits of improving jet fuel quality through hydrotreatment and the industrial, economic, and legal feasibility of doing so. As stressed by Jutta at the beginning of this webinar, the non-CO2 effects of aviation can't be ignored any longer in policy. Although the Fit 55 package has begun to address issues around transparency through introducing a monitoring, reporting, and verification system for aromatic sulfur and naphthalene, we can't stop there. The technology does exist to hydrotreat jet fuel, and new findings from the ICCT demonstrate that this would not come at an extreme cost. But throughout this webinar, we've seen that more is needed on a legislative level for this practice to become widespread. During the panel, Carly was able to provide us with some useful insights to demonstrate there are a number of further legal pathways available to improve jet fuel quality standards in the EU, for example, the fuel standard setting body she mentioned. This will be a necessary step if hydrotreated jet fuel is going to be distributed at scale. I think what's been demonstrated throughout this webinar is that it's becoming more and more evident that the benefits of scaling up the hydrotreatment of jet fuel outweigh the costs. Preliminary findings from the studies presented today by CE Delft and Transport and Environment indicate there are significant climate benefits due to the reduction of the non-CO2 effects of aviation and significant health benefits due to the reduction of air pollution around airports. I'm sure both of these studies will provide a fruitful springboard for further discussion, that this is a body of research and evidence that will only continue to grow. Today's webinar is by no means the end of the conversation. There are still some uncertainties, but this is not an excuse to delay all action. The only way to reduce this uncertainty is with more research, discussion, and transparency. We've exchanged a lot of ideas, and we must ensure that we continue this information sharing and coalition building so that we can tackle the non-CO2 effects of aviation and the air pollution effects. Thank you very much, and I look forward to further discussions. And thank you again to all our speakers and panelists.